everyone, this is Shiva. So in the previous one, at the end, I've told you that maybe not. Well, whatever it is. So this is that I would discuss the variable charge density. So here it is. So charge is being distributed within a sphere of radius capital R, with a volume charge density rho of R is equals to A by R square into e power minus 2R by A, where capital A and small a are constants. If capital Q is the total charge of this charge distribution, then radius is right. So variable charge density. So consider a sphere of radius r, capital R, and so at some particular distance r, I've imagined an elementary sphere of thickness, excuse me, of thickness dr, right, and its radius is small r. Okay, so now if I write expression, or if I take this one into account, the limits, if I take from 0 to r, then I would cover the complete sphere. Okay, so yeah, volume charge density rho is equals to q by v, total charge by total volume. So that I've written as dq by dv in differential form. So if I want the total charge, so I should integrate dv goes that side, right, rho dv. So q is equals to integral rho dv, q is equals to integral rho, the function which is varying with respect to distance that is given, and I've substituted this one there, right, and dv is the elemental shell's volume, right, the thickness is dr, and if it is r, the surface area would be 4 pi r square, and if I multiply that with the elemental thickness, that is dr, then I would get the total volume, right, which I've denoted with dv here. So I put that expression 4 pi r square dr here, right. So rho multiplied with this one, right, r square gone, right, 4 pi, a is constant, that they've given in the problem itself, right, capital A and small a are constants. So I've took it outside, right, to 4 pi a integral e power minus 2r by a dr, right. So 4 pi a integral, so limits, yeah, 0 to r, integral e power minus 2r by a, that I've did here, right, and we got this expression, right, q by 2 pi a is equals to 1 minus e power minus 2r by a. We need a relation between r, right, we need r actually. So what I took is, I took 1 this side and I reversed it again so that this minus would cancel, right. So that's what I did here. 1 minus q by 2 pi is equals to e power minus 2r by a. If I take natural logarithm on both sides, right, I get this, and if I this take r right here, a goes this side, 2 comes here, so a by 2 ln of 1 minus q by 2 pi a, right. So I've took here LCM, so 2 pi a minus q by 2 pi a with a minus sign here, and if I take it minus inside, so this one will be reverse because ln a by b, right, ln a minus ln b, and if I take reverse of that, ln b minus ln a, and if I divide this with 2 pi a, I'll get 1 by 1 minus q by 2 pi a, which is our option here, right. So this one and this one are equivalent, right. So the correct option would be this one, fourth one, right. I hope you got the idea. The elemental method, pretty standard one, right. Right. So they could ask based on line charge density or surface charge density, that is two-dimensional with respect to area one. So whatever they ask, this is the actual method, right. Take a finite element, write the expression, and compute it within the limits, then we'll get the whatever the required quantity. The same we did with force, right, a coulombic force between continuous body and point charge. Okay, so yeah, we are based on this one, the same charge density variation one. We have a pretty model which is a standard one, which is already they've given an exemplar, and the same that exemplar problem they've asked as a PYQ in mains. Okay, so I'll discuss that in the next video. Thank you very much.